In this lecture we will be looking at higher order elements for one dimensional problems, and if you recall, in the last lectures we used two node element, linear element, and we also developed the governing we developed element equations for general one dimensional problems using two node linear element, and also we have seen applications like heat conduction problems and also a column buckling problem. And in the last class or in the last lectures, when we have seen this column buckling problem, we solved this problem using 4 two node linear elements, and we have seen the critical buckling load that we obtained has about 5% error when we use 4 linear elements. So one way to improve the accuracy of the solution is to go for higher order elements. So in today's lecture or in the next 2 lectures we will be looking at higher order elements. So finite element formulation presented so far has been on linear trial solution over an element, that is we discussed about two node linear element. The main advantage of these linear elements is that they are very simple to formulate, as you have seen, but they have some drawback. Their drawback is that usually a large number of linear elements are required to get a reasonable accurate solution. So one way of improving the solution, which you have seen in the last lecture for column buckling problem, is to use more number of linear elements, but as you increase the number of elements the equation system also gets increased, because we will be having more number of nodes. So one way of improving solution is to go for higher order elements. So that is what we will be doing in this class. So this lecture presents finite elements for one dimensional problems based on quadratic and higher order trial solutions. So we have seen in the last lectures we have seen linear, so next one is quadratic, or you can go for cubic and quartic order elements. So in this lecture we will see a procedure for doing that, and when we use higher order elements, element formulation becomes little bit more complicated. However, few of these elements are required for a given solution accuracy. So even though formulation is more complicated, we can use less number of elements. So the size of equation system that we will be solving will be smaller than what we usually get using linear elements. We will be solving same column buckling problem that we have solved using 4 linear elements at the end, or once we complete the element formulation using quadratic elements. And these higher order elements are especially useful if more accurate solution derivatives are desired. If you recall, we are after the solution but not after the derivative of solution, but if you somebody is interested in derivative of solution or accurate values of, let us say, strain, so then higher order elements are very much useful in that case if more accurate solution derivatives are desired. Now let us look at what are the various general steps involved in the formulation of finite element equations. So first step is choose the element shape. It depends on the kind of problem. Line elements for one dimensional problems, for 2 and 3 dimensional problems we will be seeing in a little bit later. There are different shapes possible, like triangular or quadratic, or rectangular or quadrilateral elements, or if it is 3D you can have tetrahedron or a quadrilateral or a cubic element. And next step is choose the nodal degrees of freedom, how many nodes you want for an element. This depends on the order of boundary value problem, which dictates what are the essential boundary conditions. And if you recall, if the boundary value problem is of order 2p, those boundary conditions of order 0 to p minus 1 are essential, and those boundary conditions of order p to 2p minus 1 are natural boundary conditions. So depending on the order of the boundary value problem, which dictates what are the essential boundary conditions, the number of degrees of freedom for each element will be decided based on that. The nodal variables chosen correspond to the essential boundary conditions, because if you see a fourth order differential equation which corresponds to beam bending problem, there we have 0th order and first order equations as essential boundary conditions, whereas third and fourth order equations as natural boundary conditions. So we need at least first order continuity in the solution, or we need derivatives also for imposing the essential boundary condition. So that is what this step says, choose the nodal degrees of freedom depending on the problem that we are solving. So after these two steps, we need to obtain suitable shape functions for the chosen element, that is express all trial solution in terms of nodal parameters of that particular element. And once we have trial solution in terms of nodal parameters through shape functions, we can substitute the trial solution into an equivalent functional if you are using variational method, or if you are using Galerkin criteria, or in Galerkin criteria if you are using weighted residual method. And once we substitute the trial solution into equivalent functional or Galerkin criteria, then we can do all the manipulations like carrying out integrations. And in case of Galerkin method, the above steps gives or give the finite element equations, whereas for variational method we need to apply stationarity condition, that is differentiate the functional, which now is a simple function of nodal parameters with respect to the nodal degrees of freedom to obtain the element equations. Basically these all steps you have already experienced when we are solving problems in earlier lectures. So in today's lecture we will be looking at Lagrange interpolation formula for constructing finite element trial solutions, that is shape functions for second order boundary value problem, and also a basic concept of isoparametric mapping will be looking at it, where shape functions are used for transforming the physical element geometry into a parent element simple geometry. So we will be looking at isoparametric mapping, a quadratic element for general one dimensional boundary value problem is going to be presented, and we will be developing finite element equations using quadratic element for general one dimensional boundary value problem using Galerkin method. So once we have the element equations for a quadratic element, then we can solve any problem like we did in the earlier lectures, like we can solve heat conduction problem or under various boundary conditions, or we can solve using even the column buckling problem by just comparing or making a comparative table of the corresponding variables in the one dimensional general one dimensional boundary value problem and that specific problem. So now for isoparametric element, it is usually difficult to express element equations in an explicit form because of need to integrate complicated functions. So we will be seeing this, and also so for that because the explicit expressions are possible only if we can carry out integrations accurately, or we can carry out integrations without adopting any numerical techniques, but sometimes the integrand, when it becomes complicated, we need to adopt numerical integration. So we will also be looking at integral numerical integration schemes. One of the numerical integration scheme is Gaussian numerical integration procedure. So that also we will be looking as a part of study of these higher order elements. So now let us look at how to derive the shape functions for higher order elements or second order problems. So one of the key steps in derivation of element equations is development of shape functions that express trial solution over an element in terms of nodal parameters. For any problem, the shape functions can be derived starting from a suitable polynomial, as we did for linear elements. When we are deriving the shape functions for linear elements, what we did is we assume trial solution to be u is equal to a naught plus a1x, and we solve for a naught a1, or we expressed a naught a1 in terms of nodal parameters and back substituted this a naught a1 and grouped the terms containing nodal values, and then we got the shape function. Similar procedure can be adopted. For second order problems in which the solution, not its derivative, is nodal parameter, it is possible to write shape functions more easily using Lagrange interpolation formula. So the procedure which you have seen earlier, that is starting with a suitable polynomial, it becomes more cumbersome when you go for deriving for higher order elements. So the other alternative is to use Lagrange interpolation formula. So one point that you need to keep in mind is Lagrange interpolation formula can only be used when the solution, not its derivative, is the nodal parameter. So note that Lagrange interpolation formula will not be applicable to, for example, a fourth order problem, which is like a beam bending problem where we have both solution as well as derivative as the nodal parameters. The reason is simple, reason is being that fourth order for a fourth order problem, nodal parameters must include the solution as well as its first derivative. So now let us look at first starting with a polynomial, how to derive shape functions for a quadratic element. Derivation of shape functions starting from a polynomial, and this method starts by choosing a suitable polynomial. And how to choose the polynomial? The number of coefficients in the polynomial is equal to the number of degrees of freedom of element. If you recall, for linear element, the shape function derivation of linear element, we started with a naught plus a1x because there are only two nodes. So a naught a1 are the coefficients, two coefficients. So here if we want to derive shape function for quadratic element, we need to start with a polynomial having three coefficients, that is a naught plus a1x plus a2x square. These coefficients are then expressed in terms of nodal degrees of freedom, resulting in the shape function. Shape functions for a quadratic element, the derivation is shown. A quadratic polynomial trial solution is assumed, u is equal to a naught plus a1x plus a2x square. Why? Because since there are three unknown parameters, each element must have three nodes, so that these parameters can be expressed in terms of unknown solutions at the nodes. since there are 3 unknown parameters, each element must have 3 nodes, so that these parameters can be expressed in terms of unknown solutions at the nodes. For one dimensional problems, nodes are required at the ends of the element to ensure continuity of solution across element boundaries. Furthermore, essential boundary conditions can be imposed directly, because one of the nodes will be at the end where boundary conditions may be specified or prescribed. So, for a quadratic element, the third node can be placed anywhere over the element, and but the placement of middle node is going to influence the solution that we will be seeing once we develop the shape functions. So, a typical quadratic element is shown in the figure here, having 3 nodes, node 1, 2, 3, node 1 at x1, node 2 at x2, node 3 at x3 and the corresponding nodal parameters at node 1 u1, u2 at node 2 and u3 at node 3. The unknown solutions at nodes are identified as u1, u2 and u3. From the assumed polynomial u is equal to a naught plus a1 x plus a2 x square, by substituting x is equal to x1, x is equal to x2, x is equal to x3, we are going to get 3 equations. The 3 equations that we get by substituting x is equal to x1, x is equal to x2, x is equal to x3 are given here, and using these 3 equations we can solve for a naught, a1, a2. Solution of this system of equations can be written like this. Once we solve for a naught, a1 and a2, here the constant or the parameter c is defined like this. So, solving 3 equations for a naught, a1, a2, we got the corresponding a naught, a1, a2, and now substituting these values of coefficients a naught, a1, a2 back into the trial solution, we get this one, and this equation can be rearranged such a way that the terms containing u1, u2, u3 are grouped together. Grouping terms with same nodal unknown together, we can write the previous equation in this form: u is equal to n1 u1, n2 u2 and n3 u3, where n1 is given by this, substituting the value of c and simplifying, n1 is equal to x minus x2 times x minus x3 divided by x1 minus x2 times x1 minus x3, and if you see this n1 by substituting x is equal to x1, we notice that n1 is equal to 1, and by substituting x is equal to x2 or x is equal to x3, n1 is equal to 0. So, n1 is going to be 1 at x is equal to x1, n1 is going to be 0 when x is not equal to x1. Similarly, n2 and n3 are given by this. So, these n1, n2, n3 are called shape functions. shape functions for quadratic element. And instead of going through all these cumbersome procedures starting with a polynomial, as you can notice that when we go for when we took this quadratic element when compared to the linear element, the procedure or the effort is very cumbersome. So, instead of going through this procedure, there is an alternative way, which is a Lagrange interpolation formula for shape functions. Using this formula, we can write shape functions for a second order boundary value problem up to any order of trial solution. So, now let us look at Lagrange interpolation formula for shape functions. For second order boundary value problems, a general formula called Lagrange interpolation formula is available for writing shape functions directly without going through the detailed calculations, which we have seen in the last in the previous slide or previous slides. Remember once again that this formula is not applicable for fourth order and higher order boundary value problems, because Lagrange interpolation formula is only applicable for the case when only the solution is nodal parameter, not its derivative. So, that you need to keep in mind. So, according to the Lagrange interpolation formula, the ith shape function for an n node line element for second order boundary value problem can be written like this, where n is the total number of nodes in the element. So, using this formula we can write shape function expressions for any order element, quadratic, cubic, quartic, fifth order, sixth order or 100th order element. N is total number of elements. If it is a linear element, n is equal to 2, quadratic n is equal to 3, cubic n is equal to 4, quartic n is equal to 5, and so on. And here in this expression, note that the numerator is a product of terms x minus x1, x minus x2 dot dot x minus xn, and if you see the numerator carefully, the only missing term from this series is one associated with the ith node. X minus xi is not going to be there, that is the term that is missing. And in the denominator is a product of terms x I, because we are writing shape function for ith node, xi minus x1, xi minus x2 dot dot xi minus xn, with ith node, that is xi minus xi is missing, that is ith node term is missing. So, using this Lagrange interpolation formula we can write shape functions for any order element. And some of the important characteristics of this shape functions: ni is equal to 1 at x is equal to xi, ni is equal to 0 when x is not equal to xi, or x is equal to xj, j is not equal to I. Because of these characteristics, the ith shape function is considered to be associated with node I of element. And if you see the shape function expression for ni is a polynomial of degree n minus 1. So, the shape function for a linear element is going to be of order 1, shape function for a quadratic element is going to be order 2, shape function for a cubic element is going to be order 3, and so on. And these nodes 1, 2, 3 need not be evenly spaced. The nodes do not have to be evenly spaced, however, placement of interior nodes influence the shape functions, which we will be seeing once we solve some examples. So, here we have seen two ways of deriving shape functions. One is starting with a polynomial, suitable polynomial, or you can use Lagrange interpolation formula, but using Lagrange interpolation formula, writing shape function expressions for any order element is much easier. So, now let us take some examples and apply this formula, Lagrange interpolation formula. Using Lagrange interpolation formula, write down trial solution for a 2 node linear element with nodes x1 coordinate is given, x2 is given for a 2 node linear element, and also show a plot of trial solution or solution if the nodal values are u1 is equal to 4 and u2 is equal to 1. So, trial solution is given by u is equal to n1 u1 plus n2 u2, which can be arranged in matrix and vector form like this, where n1 and n2 can be obtained using Lagrange interpolation formula. One, you can check these expressions for n1 n2 with the expressions that you already looked at when we derived starting with a polynomial a0 plus a1x. You can notice that these n1 n2 expressions that we got using Lagrange interpolation formula are identical to that what you already have using starting with a linear polynomial. So, these are n1 n2 values. So, the trial solution is u1 times n1, n1 is substituted, u2 times plus u2 times n2, n2 is also substituted, and once we simplify this, it turns out that this is equal to 4 minus 1.5 times x. So, u approximate solution as a function of x is obtained. So, when now we are ready to plot this as a function of x, and also we can also plot n1 n2 as a function of x. So, the plot showing n1 n2 and the approximate solution are given in the figure, and note that n1 n2 are linear shape functions, and since u is a linear function with slope, negative slope, so that is how the variation of u with respect to x is going to be as shown in the plot. So, this is how you can apply Lagrange interpolation formula to get the shape functions and also to interpolate the nodal values. So, now let us apply Lagrange interpolation formula for a quadratic element. So, now let us take another example. Use Lagrange interpolation formula, write down trial solution for a 3 node quadratic element with nodal coordinates given x1, x2, x3, and also show a plot if nodal values are given u1, u2, u3. So, first step is we need to write shape function expressions n1, n2, n3 by substituting x1, x2, x3 values, because n1, n2, n3 are required for obtaining the approximate solution, which is u is equal to n1 u1 plus n2 u2 plus n3 u3, which can be put in a matrix and vector form like what is shown there on the slide. So, now n1, n2, n3 after substituting x1, x2, x3 values and simplifying, we will obtain what is shown there. So, now using these n1, n2, n3 values, approximate value of u or approximate expression for approximation of u can be obtained by substituting n1, n2, n3 and simplifying, and u1, u2, u3 numerical values are given. So, simplifying that, we are going to get u is equal to 4 minus x over 3 minus x square over 12. You can see here this trial solution is quadratic, and also each of the shape functions are quadratic. So, now we can plot this n1, n2, n3 and also the approximate solution. And you can see by looking at this, you can note that by looking at these figures or these plots, that the location of interior node, that is x2, influences behavior of these functions n1, n2, n3. Moving the interior node closer to an end will make functions change sharply near the end. Since shape functions represent trial solution, finite element solution in a region can be made to change more rapidly by moving interior nodes closer to the end nodes in that region. So, by playing with this location of interior node, we can change the way the trial solution is varying. Note the location of interior node influences behavior of these shape functions, and moving the interior node closer to an end will make functions change sharply near that end. Since shape functions represent trial solution, finite element solution in a region can be made to change more rapidly by moving interior nodes closer to end nodes in that region. So, depending on the requirement, we can do this. So, now let us go to the next concept, isoparametric mapping. The basic idea of isoparametric mapping is that shape functions are used for transforming physical element geometry into parent element with a simple geometry. So, the physical element, the actual element, we are going to map onto a parent element, and especially elements with curved boundaries are mapped onto straight boundaries. Shape function derivation, integration are performed over parent element, and this concept of isoparametric mapping is useful for one dimensional problems. However, it is crucial for development of practical elements for 2 and 3 dimensional problems, which we will be seeing in the later lectures. A typical 3 node element and its parent element are shown here. So, the actual element is having 3 nodes x located at node 1 at x1, node 2 at x2, node 3 at x3, and this actual element is mapped onto a parent element. In S coordinate system, with node 1 at s is equal to -1, node 2 at s is equal to 0, node 3 at s is equal to 1. So, the portion x1 whatever is there between x1 and x2, it is mapped to 0 between -1 to 0 in s coordinate system, and whatever is there between s2 x2 and x3, that is mapped down to 0 and 1 in s coordinate system. For one dimensional elements, isoparametric mapping essentially defines a local coordinate system. For one dimensional problems, the parent element is a line element of length 2 units with s going from -1 to 1. And also all the nodes on the parent element are placed symmetrically. In isoparametric mapping concept, the relationship between the parent element coordinate s and actual element coordinate x is expressed using parent element shape functions as follows. If you recall, for linear element, for a 2 node linear element, earlier we have derived the relationship between x coordinate and s coordinate using the formula for linear interpolation, but we can also derive that relation between x coordinate and s coordinate using shape functions of the parent element, like using the expression that is given here, x is equal to small n taking values 1 to small I taking values 1 to n, where small n is the number of nodes, ni is the shape function, xi is the location of these nodes. So, this formula is applicable for any order of element, any order element, where I takes values of all the I takes values over the number of nodes, where ni are the parent element shape function, xi are the nodal coordinates of the actual element. So, this application of this formula or these concepts are illustrated by considering a 3 node quadratic element as an example. So, now let us take the 3 node quadratic element or typical 3 node element like this. This is same as what you have seen a few minutes back, it is reproduced here. So, now the shape functions of the parent element, we need to write the shape functions of the parent element, because we require the shape functions of the parent element to get the relationship between x coordinate and s coordinate system, and we can get write the or we can get the expressions for shape functions of the parent element using Lagrange interpolation formula. So, the shape functions for the parent element can be written using a Lagrange interpolation formula. Applying Lagrange interpolation formula, we get n1 is equal to half s times s minus 1, n2 is equal to 1 minus s square, n3 is equal to half s into s plus 1. So, we got the shape functions for parent elements for node 1, 2 and 3. So, in isoparametric mapping, the relation between x and s coordinates is expressed using parent element shape functions. By this relation, x is equal to, here there are 3 nodes, so I takes values 1, 2, 3. So, x is equal to ni or n1 x1 plus n2 x2 plus n3 x3, substituting n1 n2 n3 the shape functions of the parent element we get this expression where x1, x2, x3 are the locations of the nodes in the actual element, and by substituting s is equal to -1, you can notice here by substituting s is equal to -1 in the relationship between x and s, we get x is equal to x1. By substituting s is equal to 0, we get x is equal to x2. By substituting s is equal to 1, we get x is equal to x3, which you can easily verify. And also the original geometry, which is from x1 to x3, is mapped down to a line in terms of s with nodes at -1, 0 and 1. Furthermore, note that x is expressed in terms of s. For derivation of finite element equations, it will be more convenient if we have s in terms of x. However, in general it is difficult to get the inverse mapping. You will understand in a while why this inverse mapping is required, because once we when we have derivatives like this, therefore derivative of form du dx must be evaluated using chain rule as follows: du dx is equal to du ds times ds dx using chain rule. Note that from isoparametric mapping, the expression that we have is x in terms of s. So it is easy to calculate dx over ds. So note that from isoparametric mapping, ds over dx cannot be calculated directly. So first we need to calculate dx over ds, which is also called Jacobian, and for a linear element it turns out that this Jacobian is equal to 1 over 2 L over 2, L being the length of the element, and so for higher order elements we need to first calculate dx over ds, because we already have expression or the relation between x and s. So we can differentiate it on both sides, we get dx over ds, and once we have this we can invert this to get ds over dx. But this is possible only if dx over ds is not equal to 0. This need for inverting Jacobian puts restriction on when we can use isoparametric mapping. In particular, if Jacobian is 0 anywhere in the domain or anywhere between -1 to 1, its inverse does not exist at that point and mapping does not make sense, because if Jacobian is 0, inverse of Jacobian goes to infinity. So Jacobian becomes singular. Thus in isoparametric elements we must avoid situations where Jacobian is singular. It is always not necessary that we need to avoid, but there are circumstances or there are specific cases where we require the singularity, and we will use this property to our advantage when we solve such kind of problems where singularity is required. For regular problems where singularity is not required, we will try to avoid singularity in Jacobian. For simple cases it is possible to explicitly state conditions which will make mapping invalid. So here when we say mapping is invalid, we mean when Jacobian becomes singular then mapping is invalid. So we can specify or we can come up with some conditions such a way that Jacobian singularity can be avoided. So, we will be deriving those conditions now. For a quadratic element, we have the relationship between x and s. By taking derivative of that, derivative of x with respect to s, we get Jacobian. So, that is what is shown there, and we note that, or this can be rewritten like this, and noting that the length of element is x3 minus x1 is equal to length of element. If length of element L is denoted using L, then x3 minus x1 or x3 is equal to x1 plus L, because x3 minus x1 is equal to L. So, substituting this, that is x3 in terms of x1 and L, we can rewrite the Jacobian in the form shown in the form shown in the slide. For isoparametric mapping to be valid, J must be greater than 0 over the domain 0 to 1. J must be greater than 0 over the domain s going from minus 1 to, sorry, s going from minus 1 to 1, not 0 to 1. And you can see here J is a linear function of s. So, since J is linear function of s, if I make sure that J is positive at s is equal to minus 1 and J is positive at s is equal to 1, then J is going to be positive everywhere between minus 1 and 1, and that kind of check is only possible if J is possible, because here J is linear function of s. For isoparametric mapping to be valid, J must be greater than 0 over the domain s going from minus 1 to 1. Since J is linear function of s, it is enough to check the values of J at s is equal to minus 1 and s is equal to 1. Clearly, if J is greater than 0 at these points, it will be positive over the entire domain s going from minus 1 to 1. So, that is the condition we are going to apply to get the required conditions for to avoid singularity in Jacobian. So, substituting the condition that J evaluated at s is equal to minus 1 should be greater than 0, we get that after simplification we get x2 should be greater than x1 plus L over 4, and the other condition is J evaluated at s is equal to 1 should also be greater than 0, and applying this condition and simplifying we get that x2 should be less than x1 plus 3L over 4. So, the middle node, that is x2, should lie, or x2 should satisfy these conditions. Thus, isoparametric mapping for a quadratic element is valid as long as middle node is placed such that x1 plus L over 3L over 4 or x2 lies between x1 plus 3L over 4 and x1 plus L over 4. And we can verify this. If we violate, what happens, and if we satisfy this, what happens. We can check that using an example. Write down an expression for isoparametric mapping for 3 node element shown in figure below and plot the mapping and its Jacobian. The actual element nodal coordinates are given. Isoparametric mapping gives us a relationship between x and s. substituting the shape functions of the parent element and substituting the nodal values of the actual element x1, x2, x3, we obtain this relation. Now taking derivative of this, we get this relation j is equal to s plus 3 over 2, and it can be easily verified that between s going from -1 to 1, j is always positive. Jacobian and mapping from s to s, x to s are plotted in the figure below, and you can see since Jacobian is positive everywhere, it is mapping is valid. In a s coordinate system, all points originally between x1 and x2 lie between minus s is equal to -1 to 0, and all those points between x2 and x3 lie between 0 and 1, and so the mapping is proper or mapping is valid. Now let us take a special case. Now let us take a special case or slightly modify this element such a way that node 2, which is at location x is equal to 2, is moved to x is equal to 1.5, and see how Jacobian and mapping looks like. So now we will take that example, repeat the previous example. If middle node is moved to x is equal to 1.25, and let us repeat the entire process. Isoparametric mapping becomes this by substituting the parent element shape functions and actual element nodal coordinates, and taking derivative of it, of this we get Jacobian. Jacobian is equal to 5 over 2s plus 3 over 2. So now we are ready to plot x as a function of s, j as a function of s, and now let us see those plots. And before doing that, note that j is equal to 0 at s is equal to -3 over 5. In fact, for s going from -1 to -3 over 5, j is negative, and for s going from -3 over 5 to 1, j is positive. So that you can easily verify by looking at these plots. And it can be seen from figure here that some values, that for some values of s or some values of s result in x being less than 1, which is obviously nonsense because the actual element is between x equal to 1 and 4. So the mapping, there is some problem with the mapping, so mapping is not good. So these two examples gives us or illustrate isoparametric mapping and how to check the mapping, and also what are the conditions for placing the middle node in case of a quadratic element or a 3 node finite element. So we will continue in the next class looking at the derivation of the finite element equations for a quadratic element for a general one dimensional boundary value problem and its applications.